Alright, here we go. Back to our application problems involving vectors and the dot product. We have an example here. It says a 1,400-pound SUV is parked on a hill with a 12-degree incline. I try to draw a picture of this in advance. I want to do three things. First thing I want to do is I want to write a force vector, F, representing the weight of the SUV through a single tire. Now it's 1,400 pounds and there are 4 tires. So we're going to write our force vector F in terms of I and J and assume that the weight is evenly distributed of the SUV on among all 4 tires. So that would mean that the magnitude of my force vector would be 1,400 divided by 4, which is going to be 350 pounds. Oops. 350 pounds. If I can divide right. Okay. So now I'm going to write the force vector. The force vector in this case would be with respect to coming straight down, so that would be what, 270, and that would mean that the cosine of 270 would be 0, the sine of 270. So I'm thinking that my force vector here would be the cosine of 270 degrees I plus, oh, I forgot the magnitude. The magnitude is 350. Let me fix this up a little bit. The magnitude, 350 times the cosine of 270 degrees I plus the magnitude times the sine of 270 degrees times vector J. Well, the cosine of 270 is 0, so this is all gone, and the sine of 270 is -1. So that gives me negative 350 times vector J. So that's the force, how it's determined as far as the force vector representing a single tire. Now, I want to find the component vector of this force vector F parallel to the hill. And I'm going to round to 1 decimal place. So I've got the weight of the vehicle, and I've set up my F sub 1 and F sub 2. Now, to kind of help me out along this way is that I am going to let U here, which is along the grade of the hill, I'm going to let U be parallel to this hill here, and then have a magnitude of 1. So it's a unit vector. Here we go. It's a unit vector. Okay, so F sub 1 and F sub 2 are the components of F, parallel and perpendicular to the hill, respectively. Parallel, perpendicular to the hill, respectively. It's perpendicular here. There we go. So what we're going to do here is we're going to have to take F sub 1. That's the one we're looking for, the one that's parallel to the hill. F sub 1 would be the projection of vector F on U in that direction of the hill. So this is going to be vector F dot, let's bring that dot down just a little bit, dot vector U all over the magnitude of vector U. Now remember, the magnitude of vector U, it's a unit vector, is 1, and that's squared, so that'll be 1 times vector U. So this is F, which we just stated was negative 350 times vector J. Maybe I'll write it like this for right now. 0I minus 350 times vector J dot, because I want to have both components there, times vector U. Now vector U, that's 12 degrees, so that's going to be 1, the cosine of 12 degrees plus, or I, plus 1 the sine of 12 degrees times J all over 1, because that's 1 right here, 1 squared is 1, times, I didn't leave myself enough space here, times vector u again here. So this is going to be, I'm just going to get rid of the 1's here, because 1 times the cosine. So this is the cosine of 12 degrees. Never give myself enough space. Plus the sine of 12 degrees. Hopefully you can still see this on the screen. It's a little small, but I think if you have this on the full screen that you can still see this a little bit here. So let's see, this is going to be, here, I'll bring it over here. 0 times the cosine of 12 degrees, whatever that is, plus negative 350 times the sine of 12 degrees, whatever that is. That's all over 1, so I don't need to really worry about that. And then that's going to be times, not dot product times, but times, this is a scalar, the cosine of 12 degrees I plus sine of 12 degrees j. And this mess, of course, that's 0. The sine of 12 degrees times negative 350 is negative 72.77 approximately. That's this, times this guy. Oof, what a mess. So this, if I multiply, I'm going to have to look at the cosine of 12 degrees and the sine of 12 degrees, get my calculator out, and then I'm going to multiply through by this scalar here, and I'm going to get negative 71.2, and this is rounded to the 1 decimal place here, I, okay, minus 15.1j. Does it say find the component vector? Yeah, that'll work. That's the one. That's f sub 1 right here. So even though it looks kind of like a story problem there, they just want the vector. They don't want like a description of what the vector is. Now in part C it says find the magnitude of the force required by the brakes on each wheel to keep the SUV from rolling down the hill. Well, it'd be the opposite of f sub 1. So what we'd have to do here is give a new name. Let's call it, I don't know, B for the brakes. It would have to be the opposite of vector f sub 1. So let's see, what do we want? We want the magnitude. So first things first, that would be 71.2i plus 15.1j. So the magnitude of vector B would be the square root of 71.2 squared plus 15.1 squared. And it doesn't say what decimal place, but we'll keep the same number of decimal places that we have here. And somewhere, some time ago, I did the arithmetic on this, and I got this to be 72.8, and this would be in pounds, 72.8 pounds. Now I don't have much space here, and I know it's a story problem, and you probably should write it out, something like the magnitude of the force of the brake is 72.8 pounds. That's for each tire there to keep that car from rolling down the hill. Good thing it's not much steeper than 12 degrees, but we'd have some real serious force that would have to be exerted using the emergency brakes here. All right, with that done, let's go physics. Those of you that have had physics have already done problems in which you are computing work. Well, in physics, to find work W done by a constant force F, which I've described as vector F sub 1, or vector F there, and a moving object from point A to point B along the motion, the line of motion is given by the magnitude of the force that's in the direction of the motion, times the distance that the object is moved. You guys may remember force times distance. So if I was to lift a 50-pound object, a weight of 50 pounds straight up, a distance of 5 feet, I think I can still do that. The weight required to lift the work required to lift this weight would be 50 pounds times 5 feet, or 250 foot-pounds, excuse me. It's been a while since I was in physics, 1976. All right, so in the U.S., we usually use foot-pounds. In the metric system, they use Newton meters. All right, over to this side. If the force vector F is not directly in the line of the motion, remember it has to be in the line of the motion, then we only use the component force that's in the direction of the motion. That's why sometimes we have to break a vector down into its components. So in this case, this is what's applied to the work is done. So I've got this diagram here. I drew one like this a while back. Here's this weight and here's this rope, and those are hands that are pulling the rope so that this object moves in this direction from point A to point B. If vector D is the displacement vector that the object is moved in a straight line from A to B by the force F, the work done is, now we would need this projection vector down here. It would be the work done, now remember, this is force times distance here, like these are numbers. So notice how I've got this written down. This is the magnitude of the force times the magnitude of the displacement here. Now, if we go ahead and rewrite what the magnitude of the projection is here in this terms, we would get this expression. Notice here, oops, I forgot the little thing here. It's divided by the magnitude of the displacement twice, so what's going to happen is both of these are going to cancel out. And I'm just going to get the vector for the force times the displacement vector. Now, this is going to make for some interesting applications here, but I'm out of space, so we'll do that in the next video.